Before we fall, we must understand what we're falling into. The term black hole evokes images of inescapable darkness, cosmic doom, or even science fiction nightmares. But before it was a metaphor, it was a mystery, one born not from fear, but from the mathematics of space and time. To understand a black hole, we need to journey back through history, through theory, and through silence itself. Let us begin, not with explosions or collapses, but with light. That's the question 18th century thinker John Michel posed when he imagined a star so massive that its gravity would pull back even a beam of light. Light, the fastest thing in the universe, travels at nearly 300,000 kilometers per second. It's how we see, how we measure, and how we know anything exists. Instead of seeing gravity as a force pulling objects together, Einstein revealed that mass curves the very fabric of space and time. But what if even light couldn't escape? He called it a dark star. His idea, ahead of its time, was dismissed and forgotten until Einstein arrived. Imagine a trampoline. Place a heavy ball in the center and the fabric sinks. Albert Einstein's theory of general relativity, proposed in 1915, reshaped our understanding of gravity. Now imagine a star so heavy, it punches a hole right through that fabric. For decades, black holes remained theoretical ghosts, mathematical riddles without evidence. The more massive an object, the more it bends space around it, where the laws of physics as we know them break. Smaller objects roll toward it, not because they're pulled, but because the space beneath them is curved. That's a black hole, not a hole in space, but a region where the curvature becomes infinite. Dozens more have been discovered by their pull, their shadows, their echoes in space. The first solution to Einstein's equations describing such an object came from German physicist Karl Schwarzschild in 1916. They are pillars of modern astrophysics. We photographed their silhouettes. While serving on the Russian front in World War I, he discovered that under certain conditions, space could collapse into a single point of infinite density, a singularity. Surrounding it would be a boundary, now known as the event horizon, the point of no return. But this was all math. No one believed such objects could exist in reality. To move beyond the event horizon of fear into the calm, dark center of wonder. Then, the universe spoke. In the 1960s, as telescopes reached farther and X-ray detectors peered into the invisible sky, astronomers found stars behaving strangely, disappearing, spinning wildly, emitting jets of energy. These weren't normal stars. Something was eating them. Something invisible. Something massive. In 1971, the first true black hole candidate was identified, Cygnus X-1. Since then, today, black holes are no longer myths. We listen to their mergers in gravitational waves. We name them after monsters and gods. But here, in this journey, we won't treat them as threats. We'll treat them as invitations. To fall inward is not to vanish, but to understand. This is where we begin. Gravity. It's the oldest force we've ever known. The first we feel as infants, the one that never stops pulling. We don't hear it, we don't see it, yet it's everywhere, grounding us, guiding planets, curving stars, and orchestrating the movement of galaxies. But for all its familiarity, gravity remains a riddle, not in its effects, but in its essence. What is gravity really? For most of history, gravity was treated as a pull, an invisible rope between masses. Isaac Newton gave us its mathematical face, a force between two objects, stronger when they're closer, weaker when they're far. It explained falling apples and lunar tides. It worked, but it didn't explain why. Then Einstein came. To him, gravity wasn't a force at all, but a consequence of geometry. Massive objects don't pull, they curve. Imagine rolling a marble across a stretched bedsheet. Place a bowling ball in the middle, and the marble spirals inward. That spiral isn't caused by some hidden hand. It's the fabric of space itself bending. This is Einstein's genius, seeing the invisible shape of space. Every planet that orbits, every moon that drifts, they are simply following straight lines through a curved universe. No light, no surface, just warped space-time, a silent sculpture of collapse. And where there is extreme mass, a collapsing star, a black hole, the curvature becomes infinite. Even light, massless as it is, bends when space bends. In that sense, gravity isn't something separate from the universe. It is the universe, its shape, its memory, its architecture. Black holes are gravity at its purest. Nothing else remains. They fold, and with them, so might we, gently, peacefully, into understanding. Yet here's the wonder. Black holes don't just trap, they reveal. Their existence confirms Einstein's deepest ideas. When we detect gravitational waves, ripples in space from black hole collisions, we are, in a way, listening to gravity's music. And it is soft, it is subtle, it is serene. So as we drift deeper into this documentary, into this descent, let gravity be not a threat, but a companion. Let its pull feel like a whisper, not of destruction, but of return. Because in this quiet journey inward, the rules don't fall apart. Every black hole begins with a star. Not just any star, but a giant, massive, bright, and ancient. For millions of years, it shines by fusing hydrogen into helium, releasing energy in every direction. It resists collapse through the pressure of its own light. The battle between gravity pulling in and fusion pushing out keeps it alive. But even stars run out of fuel. When its core exhausts hydrogen, it burns heavier elements, helium, carbon, oxygen, silicon, all the way to iron. But fusing iron consumes energy instead of releasing it. The balance breaks. Gravity wins. And then, collapse. Atoms are crushed. Electrons are forced into protons. Neutrons form. In less than a second, the star's core shrinks. The outer layers rebound, triggering a supernova, a brilliant, cosmic scream of dying light. But at the center, something darker forms. Not all stars become black holes. The collapse continues. Space and time fall inward. A singularity is born. If the remaining mass is great enough, not even neutrons can hold. This is the black hole's birth, not violent, but inevitable, a quiet consequence of gravity unchecked. We often imagine black holes as monstrous, but their origin is natural, a final act in the life of a star. Smaller ones, like our Sun, end as white dwarfs or neutron stars. But the truly massive, they collapse beyond all structure. These are the echoes of formation, signs that something collapsed and never returned. And they leave behind something strange. Not a body, not a surface, just a horizon, a one-way veil. We cannot see the black hole directly, but we can see what it does. Stars orbit nothing. Light bends around emptiness. X-rays flare as matter falls inward. The process is over in moments. But the black hole it leaves behind is timeless. It waits. It pulls. It whispers. And now that we understand its birth, we're ready to approach its edge. Imagine a place in space where the rules change, where up becomes inward and forward becomes forever. That place is called the event horizon. It is not a wall. It is not a thing. It has no color, no texture, no surface to touch. And yet, it marks a boundary more absolute than any prison ever built. If you watch someone fall in, you'd never see them cross. From the outside, the event horizon is where time appears to freeze. They pass the line, unaware that the universe outside has already forgotten them. They would slow, dim, stretch, like a ghost in slow motion, fading away just before the finish line. But from their own perspective, nothing strange happens. They fall. They feel. This contradiction of stillness and motion is one of the black hole's quietest mysteries. The event horizon marks the point beyond which no information escapes. No light, no sound, no signal, not because it's destroyed, but because the very fabric of space pulls inward faster than light can move outward. It is the boundary between the known and the unknowable. And yet, it is peaceful. Every step you take, every second that passes, draws you deeper, not by will, but by the structure of space itself. Crossing the event horizon does not bring pain or sudden destruction. It is not fire or collapse. It is simply beyond. The place where you no longer fight gravity. You join it. You drift. Time, from that moment forward, becomes curved inward. We don't rush in. We observe. We wonder. If falling into a black hole were possible, the event horizon would be the moment of surrender. And so here, in this chapter, we sit on the edge. What lies beyond this silent veil? To answer, we must let go. Because beyond the event horizon, we do not return. But we may finally understand. Once past the event horizon, you are no longer in the universe. You are beneath it. The outside world cannot see you. Time cannot pull you back. Every direction now leads inward, toward the singularity. But here's the paradox. The moment you pass the horizon, the fall feels no different than floating. There is no chaos, no fire, just silence. This region inside the black hole is not filled with debris or monsters. It's empty, perfectly empty, but not calm, not in a human sense. Calm here is alien. Here, calm means fate. No choice, just descent. Space-time itself tilts inward, and you ride its slope like a drop of rain sliding down a funnel. To an outside observer, your fall takes forever, but to you it feels brief. A moment, a blink. You cannot stop, and you cannot turn back. And as you fall, something strange happens. Time stretches. A final path in space curved so tightly, there is only one way forward, and it leads to the heart. The inside of a black hole is not death. It's a destination, the singularity. But before we reach it, we linger here, inside the shadow, where the stars no longer shine, and yet something deeper than light begins to glow. The glow of understanding. At the center of a black hole lies a word whispered in equations, singularity. A point with no width, no height, no depth. A place not in space, but where space ends. Not a time, but where time dies. What is a singularity? It is gravity unchained, density without limit. A moment where all our understanding collapses into nothingness. A place where even the best theories, Einstein's, Hawking's, quantum mechanics, step back and say, we don't know. Imagine all the mass of a collapsed star compressed into a point smaller than a grain of sand. Then imagine the fabric of space wrapped so tightly around it that direction loses meaning. You cannot see the singularity. You cannot touch it. You cannot slow your fall toward it. It is the future, and you are destined to meet it. In this chapter, there is no light. The silence here is absolute, not absence of sound, but the absence of causality itself. No cause leads to effect. Time folds so tightly that moments lose order. Past becomes future. Future becomes trapped. No step leads to a next. Some physicists believe singularities are where the universe began and where it might end. A black hole's core is its mirror, infinite density collapsing inward. The Big Bang was, in essence, a reverse singularity, infinite density exploding outward. Others believe the singularity is a flaw, not in the universe, but in our math, a placeholder for where our tools fail. What happens if you reach it? Your body would not survive. You'd be pulled thinner than atoms. Your mass would join the singularity's total. You'd become part of its gravity. You wouldn't feel pain. You'd simply cease to be, in any form we recognize, like a cosmic hologram. Or perhaps it escapes in radiation. Faint, whispering. But what of information? Because time, debate, and even thought have no ground to stand on. A mirror showing us the limits of what we know. A warning and a promise. Stephen Hawking once believed it was lost forever, a violation of physics. Later, he changed his mind. We'll look again at black holes, from space. Information, he argued, might be encoded in the event horizon. In the singularity, these debates do not matter. There is no light here, but there is meaning. A singularity is not just an end, it's a mirror, that in the heart of collapse, we may yet find creation. Next, we will rise, not from inside, but beside. Until the 1970s, black holes were believed to be eternal, silent, dark fortresses of gravity that would last forever. Nothing could escape them, and nothing could erode them. Once a black hole was born, it was thought to be permanent, unchanging. Then came Stephen Hawking. In 1974, in one of the most mind-bending insights of modern physics, Hawking showed that black holes might not be so black after all. He suggested that, at the edge of the event horizon, black holes emit faint radiation. Today, we call it Hawking radiation, and it changed everything. To understand it, we need to visit the very quantum edge of space. According to quantum field theory, the vacuum of space isn't empty. It's alive. Tiny particles and antiparticles are constantly popping into existence and annihilating each other, momentary blips of energy. Normally, this flickering activity has no lasting consequence. But near the event horizon, something strange can happen. If one of these particle pairs appears just at the boundary of the black hole, one particle might fall in while the other escapes. In doing so, it reduces the black hole's mass. To an outside observer, it seems like the black hole is emitting particles, leaking heat into space. But there's a twist. To allow this process, the particle that falls inward must carry negative energy relative to the outside world. Over time, slowly, invisibly, over eons, a black hole could lose energy this way, shrink, evaporate, and eventually vanish. Let that sink in. Something once thought to be the ultimate devourer of matter, the final graveyard of light, might itself perish. Not through explosion or decay, but through a quiet, freezing death. Stellar mass black holes take far longer than the age of the universe to noticeably shrink. The smaller the black hole, the faster it evaporates. Even a black hole has a temperature. Even a black hole has entropy. But primordial black holes, tiny ones possibly formed just after the Big Bang, might have already evaporated. What happens to the information of everything that fell inside? If they ever existed, their final burst could be visible as a flash of high-energy radiation. Hawking's idea fused quantum mechanics with general relativity, two great pillars of physics long considered incompatible. In that synthesis, he revealed not just a mechanism of decay, but a deeper truth. Even the most extreme objects are not beyond the laws of thermodynamics. This realization opened the door to a new field, black hole thermodynamics, and with it, one of the greatest puzzles of our time, the black hole information paradox. Because if black holes evaporate, is it erased, a violation of quantum law? Is it smeared across the event horizon? Encoded in subtle correlations in the Hawking radiation? Is there a deeper theory, waiting to be found, that unifies both gravity and quantum mechanics completely? We don't know. But the fact that a black hole, something that swallows stars, can slowly fade away like a dying ember, is strangely beautiful. It reminds us that even in the darkest corners of the universe, there is motion, there is change, there is time, and in time, even the infinite can end. So as we continue our descent, or perhaps now, our return, we carry with us a new question. If black holes can die, what does that say about the universe itself, and us within it? There is a rule in quantum mechanics. Information cannot be destroyed. Not just data on a hard drive, but the fundamental details of particles, their spin, position, energy, all must be preserved. Yet black holes challenge this. When something falls into a black hole, it disappears beyond the event horizon. Its mass adds to the whole, but the details, the information, they seem to vanish. This is the heart of the information paradox, one of the most puzzling debates in modern physics. Hawking's original theory of black hole evaporation predicted that as the black hole radiates away, it eventually disappears entirely. The particles it emits, the Hawking radiation, appear random. They carry no clues about what fell in. No fingerprints. No echoes. Just heat. If this is true, it means that the information about everything that fell into the black hole is erased from the universe forever. But that violates the core of quantum theory, the idea that information is always conserved. And so, the question emerged, do black holes lie? Do they truly destroy information? Or is it hidden, encoded, preserved in some form we've yet to understand? This paradox sparked decades of debate. Physicists split into camps. Some argued that information is lost, that black holes create exceptions to quantum rules. Others insisted that it must be preserved, somehow, perhaps encoded in the correlations of the Hawking radiation. One idea is the holographic principle, that the information about the 3D volume inside a black hole might actually be stored on its 2D surface, the event horizon, like a cosmic projection, where the surface tells the story of the inside. Another proposal comes from string theory and the idea of fuzzballs, where no true singularity exists, and instead the black hole is made of tangled strings that retain information and structure. Still others suggest that when a black hole evaporates, the final burst, the last flicker of Hawking radiation, carries a final encoded message, a whisper of all that was. Recently, research into quantum entanglement and wormholes, even ideas like ER equals EPR, have pointed to strange possibilities, that connections between particles and space-time might hold the key. And what if the universe itself works like a vast quantum computer, where no bit is ever truly lost, only scrambled beyond recognition? We don't yet know, but the question, do black holes lie, isn't just about black holes. It's about trust in the laws of nature. It's about whether the universe forgets. It's about us, too. And maybe, are we remembered? Is every breath, every moment, every collapse and creation encoded somewhere? Perhaps not in memory, but in physics. We'll explore a strange idea, that black holes may not just be destroyers, but creators, and that the end of one universe might be the beginning of another. For centuries, black holes were seen as dead ends, cosmic graveyards, final chapters in the lives of stars. But what if they are something more? What if the collapse of matter into a black hole is not just an end, but a beginning? This idea has captured the imagination of physicists and philosophers alike, that black holes might not only destroy, but also create, that beyond their crushing pull lies not just singularity, but genesis. Let us start with a simple question. What happens after the singularity? Quantum theory, for all its power, goes silent. It's here that speculation blooms. No one truly knows. The laws of physics as we know them cease to operate. General relativity breaks down. One theory suggests that the core of a black hole could bounce, that instead of ending in a singularity, the collapse might rebound, creating a new burst of space-time on the other side. This rebound, in theory, might resemble something familiar, a Big Bang, a brand new universe. If so, then every black hole in our universe might be a wormhole, a tunnel, leading to an entirely new cosmos. But perhaps imagine that. Countless black holes dotting the universe, each one harboring a separate reality within it. Each one containing stars, galaxies, laws of physics slightly different from our own. Each one birthing something new from something old. We would never see these newborn universes. No light escapes back through the hole. They grow, expand, and evolve. And perhaps, within one of those daughter universes, black holes form again. This idea leads to a radical vision known as cosmological natural selection, that universes which produce many black holes might be more likely to spawn offspring universes. Over time, the multiverse would favor cosmoses optimized for black hole creation, like an evolutionary tree of reality, branching from singularity to singularity. A cosmic forest growing from darkness. Certain models of quantum gravity, such as loop quantum cosmology, offer mathematical frameworks. Could our universe be the child of such a process? The idea is speculative, yes, but grounded in our search for a theory of everything. That from the end of time comes the beginning of time. Could we, our stars, our atoms, our thoughts, be the legacy of a black hole that collapsed long ago in a different cosmos? And ask what black holes mean not just for the universe, but for us. It's a poetic thought, but also a scientific one, because this possibility is not entirely science fiction, where black holes give birth to new universes. And it offers something rare in black hole physics, hope, that from the most violent collapse comes not just silence, but structure. We often imagine black holes as erasers, but perhaps they are also pencils, writing new realities far beyond our view. In the next and final chapter, we'll return home to our own night sky. What do they teach us about the nature of limits? And what happens when we, too, reach the edge? In the end, black holes are not just about gravity or stars or space. They are about limits. They mark the boundaries of physics, of time, of knowledge itself. At every stage, they force us to ask questions we thought the universe had already answered. What is time? What is space? What is information? What does it mean to observe, to fall, to disappear? But more than that, they hold up a mirror. Because when we stare into a black hole, into something so absolute, so unreachable, we begin to see ourselves reflected. We see our curiosity, the relentless need to understand what lies beyond the veil. We see our fear, the trembling before the unknown, the uncontrollable, the infinite. We see our wonder, the awe that something so alien can still be governed by laws we begin to glimpse. Black holes remind us that the universe is not only larger than we think, it is larger than we can think. And yet, here we are, thinking anyway. From ancient stargazers to modern physicists, from myths of cosmic dragons to Einstein's equations, we've always looked to the heavens for meaning. And black holes, they answer with silence, with mystery, with questions that loop back on themselves. In their darkness, we find the brightest edge of human thought. They teach us humility, that our theories are only as good as the questions we dare ask. They teach us ambition, that the journey into the unknown is worth the risk, even when there is no return. They teach us imagination, that physics, at its frontier, becomes poetry. Not just scientists, but artists, dreamers, poets. Maybe that's why black holes have captivated so many, because they embody something deeply human, the desire to understand, even what cannot be seen, to chase, even what cannot be caught, to imagine, even what cannot be known. And in that pursuit, we stretch the boundaries not just of science, but of ourselves. We become more than observers. We become participants in the great cosmic story. So as we close this quiet descent, this fall into shadow, silence, and singularity, remember, you have traveled across time, across matter, across the edge of space. And even though you cannot escape a black hole once inside, your thoughts just did. They reached out, beyond the horizon, into mystery, into meaning, into awe. Sleep now, and let the universe dream through you.